We talked about how nuclear fusion, nuclear fission, and types of balanced equations. In a nuclear fusion balanced equation, there are examples like the isotopes of hydrogen atoms that they fuse together, and it creates heavy elements like helium, and it produces a lot of energy. The other method of nuclear fission is where like atoms like krypton and barium release energy. And the numbers refer to the atomic masses of the respective isotopes. In this mass balance equation is transformations that show how the energy release is equal to the loss of mass.
Rogue electron. Each pair of dominoes represents a compound. When the rogue electron hits the compound, it breaks off into two new compounds, represented by this.
For nuclear fusion, you have anywhere from 2 to a billion atoms, and they overcome the force of electromagnetic force and become one atom. But in that process, they release 2 or more beta particles, which create tons and tons of.
The difference between a nuclear and chemical reaction is that in a chemical reaction, where the atoms will have ionic, covalent, or metallic bonding, they will share, give, or cool their electrons. But in a nuclear reaction, when they do this, it gives off like a lot of energy, unlike a chemical reaction where it doesn't. So like, for example, chemical reaction would kind of be like that. I mean, not much energy is given off. But then in a nuclear reaction would be like this. Different energies with chemical and nuclear reaction. In a chemical reaction, there is not much energy given off. It's not much. It would be kind of like this. Not much energy. But in a nuclear reaction, there's a lot of energy, and it's very hot and it's very heat, so the energy would probably be like this.
By itself would be kind of like a radioactive isotope, just in itself, and this would be the full radioactivity of before its first half-life. Okay, so after one half-life, you can still see it, you probably still die from radioactivity. 2 half-lives, it's still there, as you can see, its light's still shining through. 4 half-lives, it's still kind of shining through. 8 half-lives, it's still shining through, but barely. At 16 half-lives, you can no longer see the light, but everyone knows it's still there, and seeing this would be kind of like being able to live through the radioactivity. It's still there, but you can survive it. So, after enough half-lives, you can survive almost any radioactivity. Testing of such chemicals and stuff. They've been used as measurements and radiography and trace applications. They've been used in medicine for medical diagnosis, therapy, and radiopharmaceuticals. Okay, there's also another thing that radioisotopes do. They help produce and generate electricity. Okay, the nuclear radioisotopes produce weakly penetrating radiation that can easily be shielded. A specific power of at least 0.2 kilograms will be needed for it. And radioisotopes have good corrosion resistance, so they don't corrode away and just kind of die off. They can be dissolved in water, so they're less radioactive.
Okay, I'm going to talk about the risks and benefits of each type of decay. For example, alpha radiation is most harmful when swallowed into the lungs. It's harmful because it affects the lung tissue, so it hurts your breathing. For beta particles, it's less dangerous than alpha, but it can go through your skin. It's not too much. I mean, it kind of goes through your skin, but it really doesn't do much, only a few feet. And then, like, gamma beams, what they do is they're used at, like, the doctor's office to take, like, scans of you, so it can penetrate your whole body.
Blind nuclear energy reaction. For example, when you have one rogue neutron, it hits a uranium atom, which produces 2 or more rogue electrons. Those 2 hit 2 more atoms, create 4 rogue neutrons, so it doubles each time you start. the reaction. Another one is when you take two or more atoms and combine them into one particle are given off. So the more atoms you have combined, the more particles you will fly off.
How using chemical reaction, like the atoms produce change. For example, the main one is electromagnetic force, which is at opposites they're like not the same, they're opposites attract. Then there's something called weak force. Weak force is what holds a proton and electron within a neutron. And the strong force is what holds the neutrons within the nucleus.
By Jared, Nick, Spoden, and myself. This is our ninth grade science project. Thank you.